All right, it seems to be working better if we put things over here, so let's put things over here. So welcome back to Teachers of Scholars Lecture 3. So we're going to start doing some of the mathematics needed for RSA. So RSA is coming from the first letters of the last names of the three people behind it. I will leave that as a Google assignment to figure out who they are. A lot of this was actually known before they did their seminal work, but not surprisingly, the intelligence community did not want to publicly disclose what they knew. And so I've heard stories that the NSA has mailboxes with sealed envelopes with work by some of their mathematicians just to establish their priority that they have discovered some things. But even after somebody discovers things, you can't say, we've known that for the last 10 years, because if you do, then that means people will know that for the last 10 years, you've had the ability to read what they were doing and act accordingly. So you have to be very careful, when do you finally disclose that you have cracked a code or cracked a secret? It wasn't until many years after World War II before it was announced how many key decisions were inspired by reading the decrypts of messages of the Germans and the Japanese. And so in fact, one of my favorite stories which really illustrates that you don't necessarily need to know an enormous amount of mathematics to make a huge impact is the Battle of Midway. So when World War II in the Pacific, where the US involvement began on December 7, 1941, the Japanese launched a surprise attack at Pearl Harbor. They did a lot of damage, but there was one key target that they did not hit. Anybody know what target that was? Well, they got a lot of our ships, but there was a certain type of ship that they got 0 of. Nope. Although they probably got 0 submarines. But these became the key ships in World War II. Not the tenders. They got a lot of destroyers. They got the battleships. The key targets were the aircraft carriers. It was the aircraft carriers. The aircraft carriers were fortunately not a pro. And as the war progressed, the aircraft carriers were extremely important in terms of being able to expand your force. At first, the Japanese felt that they were very secure that the US would not be able to attack them for a long time. You have Doolittle's raid, where we launched, I think it was B-25 bombers from aircraft carriers. And it was a shock that this could be done. They did not have much margin for error. And in fact, some of them were spotted on the way to Tokyo. Those can't be American B-25s. The Americans don't have any land bases close enough to launch a B-25. But when the Americans bombed Tokyo, it was a huge, huge blow to the Japanese psyche and mentality that their island fortress is not safe. Their capital was just attacked by America, and they wanted vengeance. And so this helped the Japanese choose what to concentrate on in the Pacific theater. And a lot of times people were making emotional decisions and choosing the wrong targets. When the British attack some of the German cities, Hitler responds by shifting in the Battle of Britain, rather than targeting the airfields, to now bombing London and trying to bomb the British civilians into submission. And so the Japanese decided, rather than continuing down in the Australia area, to launch an attack on Midway and try to really sever the US Pacific structure. We had intercepted the Japanese messages and we had cracked a lot of their codes, and we knew that they were planning an attack on something called AF-15. And we were pretty sure that AF-15 meant Midway. And if it's Midway and we know their plan of attack, there's a good chance we could lay a surprise and have a huge victory. And we haven't had a huge victory in the Pacific theater yet. Unfortunately, what if AF-15 is not Midway? What if it's another attack on Pearl Harbor, or an attack on Australia, or an attack on the West Coast? And if you go all in, and it's the wrong spot. So Admiral Nimitz says, okay, you're pretty sure? I'd like a little bit more than pretty sure. Come back when you're sure. So, one possibility is to send a message to Tokyo saying, greetings, we've decrypted most of your message, but we were wondering if you could help us. Okay, not going to happen. So what I believe was Commander Rochefort did was absolutely brilliant. One of the most brilliant ideas I've heard in my entire life. On a secure channel, they send a message to Midway. And they tell Midway to break their water pumps. And then to report either on an open channel or on a channel we know that the Japanese have broken, with all of your other laundry list of items, mention the fact that you have a broken water pump and you'll be out of fresh water in 2 weeks if you don't get a resupply. The Americans then intercept a Japanese message. The Japanese message says, we've just intercepted an American message. AF-15 has a broken water pump, and will be out of fresh water in 2 weeks if they're not resupplied. And at this point now, the Admiralty is convinced and willing to go all in. And this was the battle that turned the tide of the Pacific War. The Japanese lost, I think, 4 aircraft carriers to one of ours. We basically now had parity, but with better production, you could see the tide changing. So, one of the greatest successes of cryptography in World War II. In stuff like this, you want information to be secure, and you need to figure out how long it needs to be secure for, and you need to figure out how quickly do people need to be able to encrypt and decrypt. So we talked earlier today about battlefield situations where things need to only be secure for somewhere on the matter of minutes to maybe an hour, and what's really important is speed. And then there's other things like the plans for D-Day, the liberation of Europe, where you need things to be secure for many months. If it takes you an hour to send and decrypt a message, that's not a big deal, because this is something that's going over such a long time frame. So as we're building all of this stuff up, to try to get to RSA, we're really going to be focusing on efficiency right now. It's not enough to do something, you have to do it well, you have to do it quickly. So we're going to do a winding path that will eventually land at RSA, but along the way we're going to see a lot of math that should appear in middle school to high school curricula, and there should be some gems hopefully that you can take from this and use in classes or supplemental material. In some sense, theoretically, none of this is needed because we have algorithms to do all of this. But as we saw, the universe would die a heat death many times over before we make even a dent in some of these problems, so we need better ways to do things. So I'm going to start with polynomials. So imagine I give you 8x to the 4th plus 9x cubed minus 7x squared plus 8x minus 4. And I want to evaluate this at x equals 2. So here's my polynomial f of x. Well, if I want to calculate what happens when x equals 2, I just plug in 2 for x. And then what is the cost? Well, how many multiplications does it take to evaluate this term? Not 4. X times x is x squared, times x is x cubed, times x is x to the 4th, times, so this costs 4 multiplications, this costs 3, this costs 2, this costs 1, there's no cost there. So the cost of this is going to be 10 multiplications. The cost in additions, well, I'm going to have 1, 2, 3, I'm going to have 4 additions. Addition is much cheaper in general than multiplication. If you think of your 2 10-digit numbers, to add them, okay, that's on the order of 10 operations, maybe 20 with carry. But if you think about how many multiplications are with the digits, addition is so much cheaper, we're not even going to worry about the cost of addition. We'll assume addition is essentially free. And we want to know how expensive is something. Well, if instead of giving you something of degree 4, if I gave you something of degree 5, I would have a 5. And so in general, if it's degree d, it's going to be d plus d minus 1 plus 3 plus 2 plus 1. And so does everybody know what that sum is?
Yeah, it's this formula.
Yes. It's d plus 1 over 2. There's a lot of ways to see this. The story is that Gauss's teacher, when he was very young, was just having a bad day and wanted to shut the little tykes up and said, add the numbers from 1 to 100, expecting to have some time to just regroup. And then a moment or two later, Gauss says, 5,050. So the fast way to do this is you write the numbers in reverse order. And so that's d plus 1, d plus 1, d plus 1, d plus 1, and you have d of them. So it's got to equal d times d plus 1, but I've now double counted everything, so I divide by 2. So that's one way to see the answer. You can also prove it using induction. One of the themes of today is order of magnitude estimates. Can I figure out the growth rate? So really, the important part here is that this is, 1/2 d squared plus 1/2 d. So it's growing quadratically with d. If I double d, it's going to take 4 times as long. If I triple d, it's going to take 9 times as long. So the question is, can you quickly get a sense of how long this will take or how big this sum will be? Well, whenever you have sums, or whenever you have a problem, we've been talking about extreme cases. So I want to sum 1 plus 2 plus d. Can somebody give me a lower bound? Okay, 1 is a lower bound. You can do a little bit better than 1 as a cheap lower bound, though. D. Right?
Oh, right.
Right. So 1 is absolutely fine. Well, 1 is fine. 1 is fine.
Obviously D.
But D is a better lower bound.
Yeah.
Can somebody give me an upper bound? You can, well, d squared. Each term is at most d, and I have d terms, so it's at most d squared. So we know that this sum is somewhere between d and d squared. Unfortunately, there's a big range between d and d squared.
Sure.
So we want to do a little bit better job. So here's a better lower bound. It's at least d halves times d halves. And the reason is, I'm not worrying about is this an integer or not. Just look at the second half. Look at the numbers from d halves plus 1. All of these numbers are at least d halves, and I have at least d halves of them. So the lower bound would be take the second half, replace every number by d halves, and there's at least d halves of them. So you get d squared over 4. Now it's somewhere between d squared over 4 and d squared. It looks like it's going to be of order d squared. You can do a lot more with this. You can get more refined estimates. You can actually play games like this to estimate how large is n factorial. There's a lot of great stuff you can do. But what I love about this is when you're trying to work with students, here's the formula, and you need some insights sometimes to figure out exactly what is the formula. But for a lot of things, just a quick order of magnitude estimate is enough. And we can get order of magnitude, it grows quadratically in D without too much trouble. So this is an expensive algorithm to use as the degree gets larger and larger and larger. If you've ever seen pictures of fractals, you have to evaluate polynomials many, many times over. And expensive algorithms like this slow down your computer in terms of what you can do. So there is a much better way to evaluate polynomials. And so I'm curious, does anybody know the faster way to evaluate polynomials? It was taught when I was young, but I think it's gone out of fashion a lot. Begins with an H? No? Horner's algorithm? So I'm going to prove Horner's algorithm with pictures. So I'm going to take this polynomial, and I'm going to write this as 8x plus 9 times x minus 7, parentheses are getting bigger and bigger, times x plus 8 times x minus 4.
What? Really?
Really? This is one of the greatest advances in all of mathematics.
Oh my God, that's so cool.
It's the, look, if you spit out 8x squared, 8x cubed, 8x to the 4th.
Yeah.
9x, oh no, is it Verizon now?
Yeah.
9x squared, 9x cubed. The next one is negative 7x squared.
Wow.
So it's the same. Let's count multiplications. 1 multiplication, 2 multiplications, 3 multiplications, 4 multiplications. So the cost is 4 multiplications. Or in general, the cost is d multiplications. And here, in general, it's roughly d squared over 2 multiplications. a tremendous savings to use grouping. So we're talking about order of magnitude runtime of algorithms. And so we're just doing Horner's algorithm, where if you group things with parentheses, you can run things far, far faster. So it doesn't seem like this is that big of a deal. But it is tremendous how valuable this is. If someone could flip on the lights, that might help with the video, as we seem to be losing the sun. Thank you. Okay. So any questions about this? So what I love about this is it illustrates that you can take something you've seen all your life, and you've been doing all your life, and there could be an inefficiency. There could be a way to do it far better. And when we look at the runtime of algorithms, something of order D versus D squared, it's tremendous in terms of what this allows you to do. There are so many generalizations of stuff like this. In linear algebra, there's faster ways to multiply matrices than you've been taught. There's the Strassen algorithm, which is far, far faster and is tremendously valuable. As an aside, we were talking a little bit about Babylonians with some people with clocks. And so the Babylonians have bequeathed many things to us, including a love of the number 60. So whenever you have kids who complain about all the stuff they have to learn, you could remind them what it would be like to be a young Babylonian scholar where you work with base 60. And so we have to learn our multiplication table. So what would be Babylonian? So you would have x times y, and you'd be going base 60. So how many things would you have to memorize? Naively, first answer. How many products would you have to memorize? 60 times 60. So you have to memorize roughly 3,600. But then you realize it's not that bad. What's the saving you can do for multiplication? Commutative. X times y is y times x. Now you still have the diagonal, but so it's really about half of that. Not quite, but approximately. Even still, however, on the order of 1,800 is a lot to memorize.
Not to mention your character.
Yes, not to mention all the different characters. So the Babylonians had a tremendous way of multiplying numbers, and it's worth seeing. Sometimes it makes sense to take a step backwards to take 2 steps forward. So x times y is x plus y squared minus x minus y squared divided by 4. Or you can do xy is x plus y squared minus x squared minus y squared over 2. But the top is much better. When you expand the top, you'll get x squared plus 2xy plus y squared. You'll get x squared minus 2xy plus y squared. So the x squareds cancel, the y squareds cancel. You get 4xy divided by 4. So rather than multiplying 2 numbers, I'm going to add 2 numbers, subtract 2 numbers, square that, subtract, and divide by 4. And this is a good idea. Why is this a good idea? This seems far worse than just multiplying x and y. Why would you do this? Okay, so what's the advantage of knowing squares? How many squares do I need to learn? You have to learn, but I'm saying there's far fewer squares than general multiplications. So if I need to do squares, maybe that's on the order of 60 or maybe 120 because I'm going twice as high. So I don't have to learn as much. Or even better, what you can do is you can have the lookup table. Anything that you're going to do a tremendous number of times, you can just write it down. This is how cell phones and a lot of other devices can be so quick. There's certain calculations that are just stored and they can call from memory. And then other things they have to recompute live. But for this, you can have a lookup table. And if you consider the cost of carrying all those clay tablets, you want to minimize how much you have on you. And so it's much better to do 2 squares, even after an addition and a subtraction, and then do another subtraction and a division by 4, than to go through and have to learn all the different ways of multiplying 2 numbers. Theoretically, No, but from a practical point of view, this is much better. And it turns out in some things in advanced mathematics, looking at combinations like this is actually theoretically useful as well. So there's some theoretical advantages of being able to express things like this. But the whole idea is to be able to do a calculation efficiently and well. So this will eventually lead into RSA. We just mentioned Horner's algorithm. And so I give you a polynomial, and I'll write it maybe, an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. So that's the most general polynomial of degree n. I have n plus 1 unknowns. So the cost is n multiplications. I don't care about additions. Do you think that there's a better approach than Horner's algorithm? Do you think we should be able to evaluate this in less than n multiplications?
Yes, because you're asking the question.
Years ago, when I was a postdoc at Brown, I had fun with my students many times, but I think my most enjoyable moment was an abstract algebra exam. I think it dropped their lowest exam, so I didn't feel too bad about doing this to them. It was a life lesson. There's something in mathematics called a ring. And certain rings have other properties. One nice property is to be an integral ring. And I gave them a set with some options, with some operations on it. I asked them for 5 points, part A, is it a ring? And then part B, for 15 points, is it an integral ring? 2/3 of the students wrote, it must be a ring, else why would you ask part B? It was not a ring. It failed the closure property, which is the most easiest to check, which people always forget to check, because of course it's going to be closed. So I deliberately gave them an example where it was not closed, but if you assumed it was closed, then yes, it was a ring. Everything else worked, and then it would be an integral ring as well. So for a lot of things, your logic is correct. And in fact, the first part of today, we had a lecture on the German tank problem. Who do you think does better, the mathematicians or the spies? Since I'm giving it, the correct answer is clearly the mathematicians. But do you think that there's a way to do this in fewer than n multiplications with general values of a0 through an? Do you think we should be able to?
I have heard the phrase that something sort of on the order of difficulty, there's polynomial
Right.
difficulty versus some other things.
So
I'm guessing that no, that's what it is.
well, that is a slightly, that's measuring how long things are. And so this would be polynomial in the degree.
Why didn't you say this n multiplications? A minute ago, it was like 4 plus 3 plus 2 plus 1.
Oh, so, right, but we used Horner's algorithm.
Oh,
So with Horner's algorithm.
Using Horner's then. Okay.
Right.
Right.
I mean, once you do Horner, you're not going
So
back.
you're looking at anything better than n.
Could you do better than Horner? Do you think there's any way to do this in fewer than n?
It doesn't jump out at you.
It doesn't jump out at me either.
No.
There is a great story of somebody who fell asleep in a graduate class and woke up and saw 10 problems on the board and thought that that was the homework assignment. And then a week later goes to the professor and says, this is the best I can do. All right, fine. And the professor I have seen documentation that this is a true story. The professor contacts the student a week or two later, because the professor was very busy, took a while to get to the homework. It wasn't homework. The professor had written the 10 most important problems in the field on the board, and the student was only able to solve 2 of them. And, okay, you're writing this up now.
Yeah.
At a PhD from Stanford. So sometimes your mindset can impact whether or not you can do something. If you are told it's hard, what I just heard is, you're going up to the majors and you see, oh my God, Nolan Ryan is on the mound. Oh my God, I can't do anything against Nolan Ryan. Or, oh, he's old, he's past his prime, he's going to get. It's how do you view what's going to happen? And so for here, we have n terms to deal with. I don't see any way to beat this, because I need to get all of these values. But maybe I can do better than n multiplications if I stop looking at a general polynomial. Maybe certain polynomials can be evaluated easier. What do you think might be the easiest polynomial to evaluate? So constant, but that's, I want something that's going to, I want a degree n polynomial. What's the easiest degree n polynomial?
X to the n?
Yeah, so let's try x to the n. So for instance, let's say I take x to the 100. I always do 100 because that's where I know exactly what to do for the next few lines. How many multiplications should this take?
99.
Should take 99. I can do it in far less than 99. Because of squaring.
Yeah.
So 100 is 64 plus 32 plus 4. This is why you always do the same example. I'm writing 100 in base 2. X times x is x squared. X squared times x squared is x to the 4th. X to the 4th times x to the 4th is x to the 8th. Now remember why I don't like doing x to the, but x to the 16 times x to the 16 is x to the 32. X to the 32, x to the 32 is x to the 64. 1, 2, 3, 4, 5 multiplications to get to here. Oh, did I skip one?
Yes.
Oh, I did. X to the 8, x to the 8, x to the 16. All right, 1, 2, 3, 4, 5, 6 multiplications to get to here. 7 to multiply these two, and then 8 to multiply that. So I can do it in 8 multiplications. 1, 2, 3. And what I'm basically doing is, I'll use the Darth Maul pen. X to the 100 is x to the 64, x to the 32, x to the 4. A tremendous savings.
Yeah.
And so the worst it's going to be is basically like twice the log of your exponent base 2. So the cost is basically at most the log of n base 2 times 2. Because worst cases I have to go all the way down and go all the way up.
Does that work for any n value though?
It works for any n value. Because I just take my number n and I write it in binary. And I never have to go more than log of n base 2 digits. And then the worst case is if I gave you 127, I would have to do 64 times 32 times 16 times 8 times 4 times 2 times 1. And so that would be the worst cost.
But still, it's a lot less than 99.
Although if you had to do x to the 127, there's a faster way to do it.
Oh, x to the 128 minus 1.
Oh, divided by x, yes.
Go back.
So if you're willing to overshoot, you're going back to sometimes it's better to take a step backwards to take a step forward. Calculate x to the 128 and then divide by x. That's much better than doing all those multiplications. So if you're willing to do that, then you can cut down a little bit on how bad things are. And then it becomes an interesting game as to just how well can you go. So this is called many things. Fast multiplication is one of them. Sometimes it's called repeated squaring. And it shows you that if you have a special structure, you can do better than the general case. Well, that's not surprising, because I have some structure that I can take advantage of. And the fact that this runs in logarithmic time, so rather than running on the order of n squared or on the order of n, it's now running on the order of log n. So, should I be excited? I am, but the question is, should I be? Well, we were talking about primes. We talked earlier today about primes that were roughly of size 10 to the 200. So anything of size 10 to the 200 should terrify you. And if you have to do something, maybe the square of p, p squared is going to be on the order of 10 to the 400. All right, let's look at the log of p, base 2. Well, that will be 200, the log of 10 base 2. Log of 10 base 2 is approximately 3 point something. A little bit more than 3 and less than 4. So this is going to be less than or equal to 400. Even if I have to square that, it's nothing. I can do something 400 times. Well, not me, but my computer. I'm not worried about something like that. And this is why we can use such large primes and still be able to do things in a reasonable amount of time, because what's going to control the growth rate is going to be the logarithm of the number. So even though the number itself is quite large, the number of operations we need to do is so small. So when you're trying to find ways to motivate students as to why should you care about logarithms, this is doable, and it's doable in real time. The students are spoiled in so many regards. One of them is streaming video. You could basically watch almost anywhere in the world streaming video where it streams well. When it first started, it would take a while to buffer and load, and you get a little bit, and then it would be frustrating. You couldn't watch a game live. And so the fact that you can do all of this in real time is tremendous. Okay, so any questions on some of this basic stuff here, this repeated squaring? We can take high powers of numbers cheaply. And that's going to be one of the key inputs into RSA encryption, which is going to allow people to exchange information in a secure way. And we'll see that there's ways to do this even if they've never met before, to exchange keys. So if you've met somebody and you agree and then you're going to go off, you can have a key book, a code book. Well, what if you've never met? So if you want to communicate with Amazon, you don't want to have to first go to Amazon's headquarters and establish who you are. You want to be able to log online and have your credit card information securely transmitted. So you need ways to send messages securely. You also need ways to check and make sure that if you get a message, it is from who it says it's from. So the math department has been hit at Williams recently twice with phishing attacks, with someone claiming to be the chair of the department. She's in a meeting, and could I please do her a favor? Oh, sure, what do you need me to do? I need you to buy 8 $100 Google cards for a gift for my cousin, and just scratch off the back and send them to me. So I know this is being recorded. I love it when I have these attacks because I like to have fun with the person. So I've actually gotten this Fisher twice, and eventually in the second second, oh my God, you did this to me again. So I wrote back, sure, happy to do this. I assume you'll just pay me back when you come back on Thursday. So I said, okay, well, you asked me to go to the store. There's no store near me. Is it okay if I just buy them online? Oh yeah, that's fine. And so I take a picture and I send them a picture. It's a black rectangle, which I label, barcode scan.jpg. They say, oh, I can't view it. Oh, it's working fine on my computer. Let me try brightening. What's the issue? Is it too dark, too bright? It's too dark. Okay, let me try lightening it up. So I send the slightly pink rectangle. I said, okay, I just put it right in the window with the sun coming on. Is this easy to read?
Use torture.
Oh, yes. We've seen your time.
But he said, I'm still not able to read it. He goes, yeah, it's fine on my end. Let me try texting it to you. What's your phone number? And so he sent me his phone number. So I passed on the phone number to OIT. I don't know, but this was the second time I got his phone number. He tried before.
Same phone number?
Different phone number I checked.
You sure it's a guy?
I know that sounds a little bit sexist, but I'm playing the odds, unfortunately, as to who are the nefarious characters in the world. But it's a terrible thing because a lot of people fall for stuff like this. One of my friends, his father, got an email claiming to be from the son's father-in-law saying, I need some help right now, quickly can you, and transferred several $1,000s because he didn't want to cause an issue in the family. And so, anything I can do to just, spread knowledge about, but, how do you make sure that a message is from who it says it is?
Very good question.
And so it turns out in RSA, not only can you send messages securely, but you can also sign them so that you can tell that the message came from who it says it is. So there's a lot of wonderful features about RSA. Other methods of encryption have replaced it in terms of the level of security they provide for the amount of computation. But one of the things that you want to keep in mind is you need to be able to prove that the message comes from the person who claims to send it. And so we are fortunate, we also have, if we don't finish today, we have a lot of time next Wednesday to go into as much the details as you want about why this stuff works. Right now what we're doing is we're just seeing some of the mathematical ingredients, and I'm not specifying exactly how they all come into play. So one of the next things we need is the greatest common divisor. How many of you teach GCDs? Okay, GCM? Oh, GCM, oh, greatest common factor?
Yeah.
Okay. Right. So this is the greatest common divisor. So you want to take as inputs x and y and return d such that d divides x, d divides y, and if e divides x and e divides y, then e divides d. So there's a couple of ways you can define the greatest common divisor or factor. Is this the definition you use?
No, I'm doing it with 7th graders, so it's nothing like that.
I'm just going to explain what that means.
No.
So if I give you two numbers, what's the largest number that divides both of them? So,
I understand the
Wait.
concept of saying 7th grade doesn't look anything like that.
well, but I'm saying, is this equivalent to what you say to them, not how you write it?
Probably.
Well, because the other thing you could do is you could also do, then E is less than or equal to D. There's two different ways to interpret what do you mean by the greatest. One is that anything else divides it, or the other is anything else is less than it. So you have to be a little bit careful as to how you define the concept. So I would define it as, if anything else divides both x and y, then it also divides d. And so you want to prove that such a number exists, that the number is unique, and then you want to prove that you can find it, and that you can find it efficiently. So it turns out finding these numbers efficiently will be useful for RSA. We need to be able to find greatest common divisor, or something related to greatest common divisors. So there's a beautiful result that if the GCD of x and y equals d, there exist a and b such that ax plus by equals d. So do you have an algorithm to find the GCD? Or? Okay. So not only does the GCD exist, but you could find the GCD by choosing an appropriate A and B. Now it turns out A and B are not unique. So imagine AX plus BY equals D. Let's look at A plus 8BX plus B minus 8AY times, 8BY times X, and here I'll want B minus 8AX times Y. Well, if I multiply this out, I'm going to get AX from this, and I'll get BY from this. I'll get 8BYX, and I'll get minus, did I do it right? I think I put things in the wrong spot. I want the A outside here, and I want the B outside here. So when I multiply it out now, I'll get A times 1 times X, that's my AX. B times 1 times Y, that's my BY. Now I'm going to get an 8ABYX and 8ABXY with a negative sign, and so they cancel. And so this will just be AX plus BY, so this also is equal to D. So what this tells you is your choices of A and B are not unique. There's more than one that work. Well, instead of shifting it by 8, I could have shifted by 7 or 11, by any number. So I can keep adding multiples. So what you want to do is, in some sense, you want to figure out what is the minimal thing you could add. And so what's the smallest range we can move A and B in? And so you can start playing games like this. And this is very similar to the clock arithmetic we did. 10 plus 5 is 3. Once you go past 12, you can just reset the count. And so when I'm looking for something like this, I can shift A down and I can shift A up and B down. And so I can try to do this to get them in a certain range. Okay. So it turns out there's a lot of ways you can prove an A and a B exist. And you can also construct ways to find them. And so this gives an opportunity to talk about the difference between an existence proof and a constructive proof. Constructive proofs are wonderful. And the easiest way to show something exists is to construct it and say, here it is. It's hard to argue with something right in front of you. It's much more of a challenge when you have this existence proof, which shows that the object must exist. I can't exhibit it. So imagine you are hired as a consultant for the 2020 presidential campaign of one of the candidates. And you go to your candidate and say, good news, I've proven that you have a strategy for 270 electoral votes. Wonderful, what is it? Well, it's an existence proof. I'm sorry? It just proves that there is a way for you to get to 270 electoral votes using the resources you have. I can't tell you what the actual strategy is, no. Yeah, you're not going to get the job. In a situation like this, you want a constructive proof. So I will give you an example of a really fun game that you can play with your students. I will prove to you that player 1 has a winning strategy without being able to give you what that winning strategy is. I will prove that player 1 must have a winning strategy. And it's called the game of dots. There's lots of dot games, and the whole point of this is to give you some examples that you can take back to your students that don't require huge amounts of mathematical prerequisites to really illustrate the concepts. So this is how it works. You have a bunch of dots in a rectangular grid. The dots have gone off their diet extensively. And the way it works is last mover loses and eat all to the right and above. So on your turn, if I chose this dot, I would eat everything above and to the right. So I would eat all of those. So if that was my first turn, I would eat all of this, and they would now be gone. If the second person chose this dot, you would eat everything above and to the right. And you keep playing until no moves are left. Clearly, you don't want to have whoever moves last wins. Why would you not want to have whoever moves last wins? Yeah, you would just choose down there, and the game is really boring. It's on the level of tic-tac. If you've ever played tic-tac, it's not a hard game. In fact, as long as you play legally, you have to win if you go first. You can't lose tic-tac. Does everybody know what tic-tac is? Okay, you know what tic-tac-toe is? Trying to get 3 in a row? Tic-tac is 2 in a row. So no matter where you go, no matter where the other person goes, you can't help but win in tic-tac. So I'm going to prove to you that player 2 will always lose if player 1 plays intelligently. There are 2 cases. Case 1, player 1 has a winning strategy. So if player 1 has a winning strategy for a given board, what should player 1 do? Use it! Okay, this is not rocket science. Do we agree that case 1 is easy? Case 2, player 1 hasn't a winning strategy. Just the way it's written on the board, it's easy to just write hasn't. So if player 1 doesn't have a winning strategy, who has the winning strategy? So it means no matter what player 1 does, player 2 has a way to win. So player 1, in a mark of great insight, goes here and eats the dot in the upper right corner. Now it's player 2's turn. Player 2 has a winning strategy. What should player 2 do?
Not take the whole board.
Wait, but what should player 2 do if player 2 has a winning strategy? Use the winning strategy. So I don't know what that winning strategy is. Let's say this was the winning strategy. So if player 2 goes here, let's assume player 2 can win. Okay? So player 2, if they go there, they'll win.
Player 1 could have done that.
Player 1 should have just done that on their first turn.
Okay.
So if player 2 has the winning strategy after player 1 goes here, player 1 could have just gone there on their first turn.
But they didn't know the winning strategy, so how could they do that?
This is an existence proof.
Oh, okay.
So instead, player 1, and we'll change it from green to orange. I feel like this is Potter and they're now changing which house is won. Player 1 should now go there on their first turn.
But they don't have a winning strategy.
Well, this was assuming player 2 has the winning strategy. So if player 2 has the winning strategy, player 1 could have gone here.
Yeah.
Player 2 would go here and win. So player 1 should just go there.
Okay.
That contradicts our assumption that player 2 has a winning strategy.
Okay.
So case 2 doesn't happen. So player 1 will always win if they play intelligently.
Okay.
The problem is we don't know what that intelligent play is.
Aha.
The assumption is that one of them has a winning strategy.
One of them has to have a winning strategy in a finite game like this. Because every time you move, you make the board smaller, the game will end after a finite number of turns.
But that's not a strategy, because if two monkeys play, the same thing will happen.
Well, what this is saying is that if you did a brute force computer analysis and enumerated every case, then you would be able to find what the strategy is for any given board size. But I don't know how, if you just tell me what the dimensions of the board are, to determine what player 1's strategy should be. I know player 1 will win if player 1 is playing intelligently and correctly, but I don't know how to find that other than a brute force enumeration. So I had a thesis student last year whose task was to analyze a game I created involving Fibonacci numbers. If you're interested, email me and I can send you the article. I wanted to beat my daughter. And so I said, your thesis is to find what should I do to beat my daughter. And she proved that as long as you don't start with n equals 2, because the n equals 2 game is trivial, any other game, player 2 always has a winning strategy. Her proof is non-constructive. Really? So, done it. So I actually pulled my daughter from school so that she could come to the thesis defense, and they played live as part of her thesis. And unfortunately for my daughter, she realized as soon as she had done it, because she was playing as player 2, she made a mistake and she realized it too late, and she lost. Later that day, we were actually talking with a prospective student to Williams, and my daughter took him down, and he did not end up playing. So this is just really elementary math, but it illustrates a terrific point, that we can frequently prove that we can do something without knowing how to do it. And for some things, if you've taught calculus, how many people here have taught calculus? All right, so I'll focus over here. So if you get to like the mean value theorem, there is a point with this point. I don't know where that point is, but the point exists. And for a lot of the proofs in calculus, you only need to know that the point exists, and then you can argue and get other consequences like the fundamental theorem of calculus. And then at the end of the day, you have a result that you can use, even though an intermediate step was non-constructive. So here, it turns out for RSA, it's not enough that the GCD exists. It's not enough that there are some A and B that work. We need to find the A and B quickly. And so it turns out that there is a way to do that. So the first way is naive brute force. Look at every possible pair A and B. Well, is there any way we could maybe cut down on the possibilities of A and B? In terms of maybe the size, maybe A can't be larger than Y in absolute value, and maybe B can't be larger than X in absolute value. And you can play some games like that, and you can just go through all the possibilities. So I'm not going to go through the brute force approach. If you're interested, send me an email, and I'm happy to send you some stuff that you can do on it. But there is a way to just go through everything by brute force and see what you get. And clearly, if A is positive, B should be negative, because we'll assume X and Y are both positive numbers. So there is at least a brute force way that would find it, but its runtime would be terrible. Its runtime would be on the order of X times Y. So if X and Y are both 200-digit numbers, this is going to be on the order of 10 to the 400. So if I needed to find the GCD using brute force, this is order X times Y. And anything that's this large is completely useless for all practical purposes. Because you should be thinking of X and Y as, say, 200-digit prime numbers. And so if it's taking this long to run, it's useless. So we want something that's going to run in logarithmic time. And so what we want to do is we want to find a way to compute the GCD quickly and get these magic numbers A and B. Anybody know what this algorithm is called?
RSA.
Not RSA. It's the Euclidean algorithm. So we will do so without loss of generality, my favorite log, we'll assume X is at most Y. One of the numbers has to be at most the other. X comes before Y in the alphabet, so let's make X less than equal to Y. So we're going to start off by writing Y is equal to, there's a couple of ways of doing this. I'll do it R0X plus R1. So I'm basically just saying, how many copies of X can I take and still be less than equal to Y? And then R1 is going to be the remainder. And what can you do? I'm sorry?
Not Q0 for quotient.
Sure, let's do Q0. Or Q1. First quotient and first remainder. Yeah, that's much better notation. Q1X plus R1. So how large can R1 be? So R1 has to be less than equal to X. Can you do a little bit better?
Greater than 0.
I'm sorry?
Greater than 0.
Or it could be 0. It could be, but there could be a remainder of 0.
So the other one, get rid of the equal.
Right, so it's at most X minus 1. Because if the remainder was as large as X, I could have increased the quotient by 1. So we know R1 is somewhere between 0 and X minus 1. And now you follow the instructions on shampoo. So, lather, rinse, repeat, right? You just keep doing it. Now, of course, if you were to follow the shampoo instructions perfectly, what would happen?
You'd still be in the shower.
Yeah, you'd be in the shower for all eternity. And when I was in graduate school, we decided to revise the graduate student constitution, and it was written by non-mathematicians. We had officers who served for 1 semester and 2 semesters. And one of the parts of the constitution said that as soon as you are elected, you begin serving immediately. And another part of the constitution said at the first meeting of the last semester of service of an officer, you elect their replacement. So since some people serve for only 1 semester, as soon as they're elected, it's now the first meeting of their last semester of service, at which point you elect their replacement, who begins serving immediately, at which point. And so technically we were in violation of our constitution, and we should have spent all of our time essentially just electing officers. So now we just lather, rinse, repeat. Now we write X as Q2 R1 plus R2. Oh, sorry, this should be a, yes. So I'm now expanding out the R1. And what can you tell me about the size of R2? 0 less than equal to R2. R1 minus 1. Because here we were using X as the number that we were dividing by. Now we're using R1 as the number we're dividing by. So, lather, rinse, repeat. we now write R2 as Q3 R2 plus R3, 0 less than equal to R1. I think this is this, I think this is right.
Is that R2, right?
Oh, this should be, oh,
R1.
so this should be R1 over here, yes. This should be R1. So we should really be writing x as R0 and y in some sense as R to the negative 1 to avoid the confusion. And so now we write R1 as some multiple of R2 plus the next thing in the sequence. So 0 less than equal to R3 less than equal to R2 minus 1. And now we would want to write R2 as some multiple of R3 plus R4. And we keep going down until eventually we get, R n minus 2 is equal to Q n R n minus 1 plus Rn. And we can keep doing this until eventually Rn is 0. If it wasn't 0, we could just play it again. And we keep doing it. So eventually we get all the way down to this is 0. And now we have Rn minus 2 is Qn times Rn minus 1. And I claim that Qn is going to be the greatest common divisor. So let's look and see what's going on. So if we start over here, let's say D is the greatest common divisor of x and y. So D divides y, D divides x. So what must D also divide? R1. So if D divides x and y, D divides R1. So we know, can I erase this part over here? So if D divides x and D divides y, that implies D divides R1. What if D divides x and D divides R1? Well, so now we know it divides x and it divides R1. What must it divide? It must divide y. Because if D divides x and R1, it divides the right-hand side. So it must also divide y. What I want to claim is that the GCD of x and y is the same as the GCD of R1 and x. And then I can just march down. So I take the greatest common divisor of x and y, and it's clearly going to divide x and R1. I take the greatest common divisor of x and R1, and it's clearly going to divide y. And if you just play with it a little bit, you can see that they have to have the same GCD. Because if not, well, if something bigger divided this, it would also divide y, and then that would contradict the GCD of x and y. So the GCD of x and y is the same as the GCD of R1 and x. Well, then that's going to be the same as the GCD of R1 and R2. And you just keep marching down. So this is the same as the GCD of R2 and R1. And that's the same as the GCD of R3 and R2. And you march all the way down to the GCD, and we stopped at 0 and Rn minus 1. Or we'll stop at, we'll do it like that. So what's the greatest common divisor of 0 and Rn minus 1? I circled the wrong thing over here. It's not the quotient. This should be my GCD. Because the greatest number that will divide both 0 and Rn minus 1 is just Rn minus 1. And so it's very easy to find the GCD here. It's just whatever number I'm left with. And then you just march up, and that's going to be the greatest common divisor. So this solves about a third of what we were trying to do. It finds a way to find the GCD. We haven't shown yet that you have these numbers A and B, and we haven't shown that it's fast. But we've at least shown here's a way to find the GCD. And the key step is to note that the GCD is preserved as you march downward. Well, now I'm not going to go through the details. If you try to expand things upward, you can see I can write a combination of if I go up one level, So I'd have Rn minus 3 is Q n minus 1, Rn minus 2 plus Rn minus 1. So Rn minus 1 is the GCD. So I now have a combination of Rn minus 3 and Rn minus 2 is Rn minus 1. I have 1 times Rn minus 3 minus Q n minus 1 Rn minus 2 is the GCD. And now I can replace R2, I'm sorry, I can just keep going upwards. So I can replace Rn minus 3 with Rn minus 4 and Rn minus 5 and just keep marching upwards. So you can just keep substituting upwards. So I really recommend you just go through this, do it with a couple of numbers, and then just do the substitution upward as you keep marching. So over here, if I were to start with R2, I'll just do this. So let's say that we stopped over here, and let's say R4 was the GCD. So we would have R2 minus Q4 R3 is the GCD. But now we know R3 is R1 minus Q3 R2. So we can go R2 minus Q4, and now we substitute for R3 as R1 minus Q3 R2 equals D. And so now I'm going to get, here's my R2 term, here's my R1 term. So we get a minus Q4 R1, and I'm going to have a plus 1 R2, and I'm going to have a plus Q4 Q3 R2 equals D. And so I've replaced R3 with R1. Now I can replace R2 with X and R1. So this would be the same as minus Q4 R1 plus 1 plus Q4 Q3, and then R2 is just going to be X minus Q2 R1. And it's getting more and more involved, but so the R1 term is going to be minus Q4 plus Q2 R1, and then I'll have a plus 1 plus Q4 Q3, X equals D. And then if I do it one more time, I can now replace R1 with Y minus Q1X. And so I'll replace this with Y minus Q1X, and now I'll have my multiple of X plus my multiple of Y equals the GCD. So you can make this work, and so not only does it prove that the GCD has this form, it actually gives you a way to find it. It would be useless for us if it wasn't fast. So let's look, worst case scenario, what's the worst thing that could happen to us for R1? What do you think the worst thing that could be?
What, given the size of your number, it's
Yeah.
a 200-digit number?
Yeah, given that we have X and Y, what would be the worst outcome for R1? It's X minus 1. What would be the worst outcome for R2? So if everything is the worst possible case every single time, it could take X steps to go all the way down. That's still better than X times Y, but if X is of size 10 to the 200, this is not so good. So what we need to prove is that while bad things can happen, bad things can't happen too often, at least with the Euclidean algorithm. With other things in life, sadly, bad things can pile on and on and on. What really saves us here is that the worst case scenario can't happen every single time. A lot of times, there's this idea called you do what's locally best, or you do what's locally worst to just analyze what's going on. And so it turns out for a lot of things, if you do what is locally best, that's not going to give you the best answer. Sometimes this is called the greedy algorithm. At every moment in time, you do the best thing possible. So there is a series of wonderful papers titled, the first one is, I think, Do Dogs Know Calculus? And the second one is, Do Dogs Know Bifurcations? And I have actually met the author of this paper and his dog named Elvis, and the dog knows calculus. Now, you have to understand that as a dog, the dog does not have the same verbal skills we do. The dog does not have the same writing skills as we do. You cannot ask a calculus problem to this dog as you would to a high school student. So you have to phrase the problem in a better way. So imagine, you have water over here, and you have the dog. So here's our dog. And you throw a stick. What path should the dog take to get to the stick in the shortest possible time? Straight line.
Run faster than it can swim.
The dog can run faster than swims. What if I threw the stick over here? What path should the dog take? Straight line. What if I threw the stick all the way over here? So the straight line has the advantage of at every moment in time, it's what is locally best. If I look at where am I and where is the stick, swimming straight for the stick, 1 second later, that will get you closer than any other path. But I claim if the stick is sufficiently far away, the dog should not swim straight to the stick. Anybody know how the dog should swim? We'll assume no current. So we'll assume that the stick is being held there. We have a graduate student who is basically forced to stay there. You can do a tremendous number of things with graduate students. Just say you give them course credit. What path should the dog take to get to the stick? You've already remarked.
Run to shore, run along.
So
swim to the shore.
Swim to shore at some angle, run along shore for a while, and then swim up. Imagine the dog can travel instantaneously on land. Well then, depending on how far apart it is, you would want to swim straight down, instantaneously transport here and come up. Because the dog has a finite speed, the dog will go at some angle and then run along here and then come back up. And so what I love about this is local best, local optimal, not always global optimal. If what you wanted to do is get as close to the stick as possible in 1 second, then what you would do is you would send yourself straight towards the stick. But if you realize that you have the ability to wait a bit, it is actually better. This is another take a step backwards, take 2 steps forward. Aim towards land. And the dog actually knew roughly what angle to run at based on how far the stick was. Phenomenal paper. So when we're trying to analyze this, the worst case is if every single time it's as large as possible. Well, if every single time it's as large as possible, hopefully we can show that can't happen. So imagine we're trying to write, y equals, q1x plus x minus 1. So imagine we're in that terrible case. Now I want to write x as q2, x minus 1 plus r2. What value do I take for q2? So I want to write x as a multiple of x minus 1, and then I'll have a remainder. What's the largest value for q2 I can take? I'm sorry? 1. I'm not going to take 0. If I take 2, it's too much. Well, I'm applying the Euclidean algorithm, and I'm saying, let's assume we're in the worst case, and let's assume R1 is x minus 1. Let's see what I can claim about R2. Is it possible that R1 and R2 can both be bad? And I'm going to show that they can't both be bad. That if R1 is really bad, R2 is really good. So if I take the case when R1 is x minus 1, then I want to write it as some multiple of x minus 1 plus R2. Well, what multiple? It's got to be 1. Well, what will R2 be? So x is equal to 1 times x minus 1 plus 1. So if R1 is x minus 1, then R2 is 1. which is really good. So it turns out it's actually pretty good if R1 is very bad. Because if R1 is very bad, then R2 is going to be tremendously good. And you could actually ask, for a given value of y, approximately what x would be worst. And it turns out that the ratio of x and y is the golden mean. The Fibonacci numbers give you the worst runtime of the Euclidean algorithm. So there's a lot of great math behind this. I'm trying to just throw out plenty of things so that if there are things you want to hear more about, you can email me. And if there are things you don't want to hear more about, I haven't bored you with it. So what we want to do is we want to show that you can't have two bad numbers in a row. This is just an extreme case. If R1 happened to be the worst possible, then we know that this is essentially the best possible. I'd love it if it was 0, but 1 is so close to 0 that I happily will take it. And so what you can show is the following. Rn is n plus 2 is less than or equal to 1/2 of Rn. So every 2 iterations, I drop at least a half. So it's not as great as dropping all the way down to 1, but if I drop a factor of 2 every single time, then it's going to take, roughly, at most 2 log x steps. And that's much cheaper than x. We're now back on log scale. Whenever we get to log scale, we're happy. So now you just need to do some algebra to show that you can't have 2 really bad cases back to back. So, case 1, Rn plus 1 is less than or equal to 1/2 Rn. Well, if Rn plus 1 is less than or equal to 1/2 n, since we know Rn plus 2 is less than or equal to Rn plus 1 minus 1, and that's clearly less than or equal to Rn plus 1, which we know is less than 1/2 of Rn, we're done in case 1. This is technically known as the no-shit case. If in your first step you already drop by a factor of 2, then after 2 steps you also drop by at least a factor of 2.
Right. Okay.
You might have to clean up the language a little bit when you're talking with kids, but if you've already dropped by a factor of 2, you've dropped by a factor of 2. Wonderful. So then the case that remains is, well, what if it's not the case? So do people want to see the algebra? Okay, so we will do the algebra. I will try not to screw it up. So case 2, Rn plus 1 is greater than 1/2 Rn. And what we want to do is now we want to show that if you're greater than 1/2 Rn, then Rn plus 2 must be really small. All right, so this is where I always look at this. So this number here is 1 less than index than this, and it's 2 less than that. All right, so I want to have an Rn plus 2 here. I'll have an Rn plus 1, and I'll have a Qn plus 2, and this will be an Rn. Okay. Now, we know that this number is greater than 1/2 Rn. And so now,
So Rn is equal to Qn plus 1 times half. Greater than half of Rn.
and then I'm going to just make a little bit more space. So we're in case 2. Rn plus 1 is greater than 1/2 Rn. So we have Rn minus 1 is Qn plus 1 Rn plus Rn minus 1. Rn plus 1. Okay. And so we know Rn plus 1 is greater than a half Rn. And we want to show that Rn plus 2 is less than 1/2 Rn. So we can start looking at things. We have Rn minus 1, we have an Rn here, we have an Rn here, we have an Rn plus 2. And we want to see what would happen if Rn plus 1 is very small. Well, we know Rn plus 1 is greater than a half Rn. So what do you know about Qn plus 2? So Rn plus 1 is more than half of an Rn. Yeah, in fact, even if it's equal to 2, you have a problem. So the only possibility for Qn plus 2 is 1. So we know this has to be a 1 here. Because this is at least 1/2 Rn. So we know Rn is Rn plus 1 plus Rn plus 2. So now, since this is more than half of Rn, then that has to be less than that. So we know, so in fact, we didn't need this line, we didn't need this line. We can just now subtract from here, and we get Rn minus Rn plus 1 is Rn plus 2. And since this is more than halfway there, the difference has to be at most half. And that finishes the proof. So every 2 iterations, you go down by at least a factor of 2. So the Euclidean algorithm is not just it's not just giving you the GCD, it's not just giving you this relationship, it gives it to you quickly in logarithmic number of steps. Okay, any questions on this? So, yes?
What is the value of the greatest common divisor?
So,
Why do we want it?
so we will see this as one of the ingredients in RSA.
Okay.
So I am deliberately not going into all this stuff. I might be shifting right now into how we use this stuff.
Is there a short answer outside of RSA? I mean, was this a valuable mathematical concept outside of topology, or?
Yes, it helps to know if numbers are relatively prime. So when we look at clocks and we're trying to figure out, we know 13 and 2 have multiples with 26. I want to figure out which numbers do I need to exclude when I was doing this affine cipher. I need to find which numbers are relatively prime. And it turns out for a lot of things, being able to have this combination is incredibly powerful. All right. So two of my colleagues, Tom Garrity and Colin Adams, have recorded a lot of math debates. And one of them, they've got E versus pi, the derivative versus the integral. One of them was the Euclidean algorithm versus the trefoil knot. And I was actually shocked that they bothered to record this. Exactly. Who's heard of the trefoil knot? The Euclidean algorithm, I mean, it should have been a slam dunk. I know there's at least one other Jewish person here. We are in a Jewish building. On college campuses, there are often debates between which is the better food, the Lec3 or the Hamantaschen. And so I and Tom Gowdy have both supported the Hamantaschen in recent years. Lec3 has historically done poorly in these debates. I think it should work its way up. First go against matzah. Once you have some wins under your belt, maybe attack the Hamantaschen. But the Euclidean algorithm, it's just incredible what it can do. Right. So let me try to explain how RSA works. So you have two people, and by law they are required to be named Alice and Bob. And there's an evil person named Eve who is trying to eavesdrop. Okay? And they want to communicate securely. And so we want Alice to send a message to Bob. So Bob, he has a secret primes P and Q. Say around 200-digit numbers. He makes public n, which is p times q. He also chooses E and D such that the greatest common divisor of E and D is 1. I'm sorry?
Remind me that E and D are prime.
They don't have to be prime. They're relatively prime. So 14 is 2 times 7, and 55 is 5 times 11. So 14 and 55 have a GCD of 1. And I want E times D to equal 1 mod P minus 1 Q minus 1. So I want two numbers such that their product is 1 when you look at a clock with P minus 1 times Q minus 1 hours. And I will keep secret D, and I will make public E. Anybody have a guess what D and E stand for? Decrypt and encrypt. And so Alice has a message M. And we've talked earlier today that messages are always going to be strings of zeros and ones or strings of numbers for us. So we'll assume that this message is less than or equal to n. And if the message is larger than n, you just break it up into blocks. And Alice wants to send a message M. And this is what Alice does, is she sends M to the E mod n. So take M, raise it to the e-th power, and imagine that that's a number on a clock with n hours, and send that. Okay? Now what Bob does, let's call this message X. Bob takes X, raises it to the D power, and looks at that mod n. And it turns out that that will be equal to M. Unless something very bad happens. It's unlikely, but it could happen. We want M to be relatively prime with n. So we will assume the GCD of M and n is 1. It is very hard for Alice to choose a message that has a common factor with n, and only has two factors, P and Q. If Alice happens to choose a message that has a divisor in common, it means she can actually pretend to be Bob from this point onward. It's unlikely that this could happen. So if she chose such a message, she would have to choose a different message to send. One thing you could do is you could just adjust the last digit, or you could keep the last digit or two free and just choose something so that it doesn't come out. But the probability of them aligning is so small, it's not worth worrying. So the first thing is to see, can this be done? Yes. I've told you exactly what to do. It's trivial to do it. The next question is, can it be done efficiently? Can I do this before the universe dies a heat death? How long is this going to take? Well, it turns out E and D are going to be also of the size 10 to the 200. So I'm going to have to raise my number M to about 10 to the 200. Can we do that?
You're doing it in mod.
I'm doing it in mod. So every time, so if I do the multiplications, every time I multiply, I can always do the mod. And that will keep the numbers from growing too large. How many steps will it take, how many multiplications will it take to compute M to the E? So it's E minus 1, which is tremendously expensive. I can't afford E minus 1 multiplications. Right? If I just multiply this naively, that's E minus 1 multiplications. Do we have a faster way to compute M to the E? Even with the mods, I can't afford the repeated squaring. So if you use repeated squaring, it's basically the log of E steps. And when every time you square, the number could get as large as n squared, but then you reduce it modulo n. So you never have a number larger than n squared. And it's only going to take you on the order of
the log of E steps. So even if E is of size 10 to the 200, that's very doable. We're talking about on the order of 400 multiplications or 800 multiplications. Nothing too bad. So this can be done very easily. What about Bob? Repeated squaring again. So Bob can decrypt the message very easily. So the cost to run this is really logarithmic in the size of the primes. So if the primes have, around 10 to the 200, then it's going to take roughly around 200 log 10 steps. So this can be done very quickly. It still takes time. And so what people would sometimes do is the alphabet ciphers are much easier to do. So what you might do is you might do the Vigneri cipher where you have a really long key phrase. So rather than just doing something short like Red Sox, the Red Sox are the greatest franchise in sports history. It is wonderful that they defeated the Yankees and came back down 4 games to 0 in 2004. Go Sox, Yankees suck. Some really long string. You send that with RSA very securely. And then once the other person has received that, then you can send the rest of the message using just the standard alphabet cipher, which is much faster and easier to do. So this is the mechanics of RSA. It doesn't explain why it works. But I need to be able to find two numbers E and D such that E times D is 1. So actually, I don't need the GCD to be 1. I don't need that. I just need E times D to be 1 mod, P minus 1, Q minus 1. Now the question is, what happens if you have an eavesdropper? What does the eavesdropper hear? The eavesdropper knows N, and they know, no, D is kept secret, they know E. And they know X. So the question is, can they figure out what M is? They know E, and what else do they know? That's a lot. That's 3 out of 4. Meatloaf sings 2 out of 3 ain't bad. This is even better.
Not much a secret.
So imagine I told you I know 8 is M cubed. Can you figure out what M is?
Yes.
Yes, this is not that hard. Right? M is 2. All right, let's do a slightly more challenging one. 81 is M to the 4th.
Yeah.
What is M? Yeah. So what you're learning here is if there's no mod N, if you knew X and E, it's trivial to find M. Let's do things a little bit harder. With a mod. So my computer is open here. So I always have to remember which order to do things.
Why do they make these things public?
Well, you've got to be able to communicate with people.
So Alice knows.
So Alice needs to be able to transmit the message to Bob, and Bob says, look, here's my N, here's the E you should use to encrypt. And the idea is, unless you know what D is, you don't have an easy way to find M. So Bob has the easy way. Now, E and D were chosen such that E times D is 1 mod P minus 1 Q minus 1. If we knew what P and Q were, we would know what P minus 1 and Q minus 1 were.
And
And
we know D.
we know D for decrypt. So we could actually, turns out we could use the Euclidean algorithm, because this is basically saying we want a GCD of 1.
Right.
So, okay, so the mod of 10 and 4 is 2.
So if we can figure out P and Q, we can figure out D. And we can decrypt it like that.
Okay. So 38 is equal to M to the 13 mod 55. what is m equal to? So this is called the discrete log problem. And the reason it's called the discrete log problem is this is basically, look, just take a log of both sides. If I take the log of both sides, I can solve for m. Take the log of both sides, I can solve for m. But here, because of the mod, it jumbles things up. This doesn't mean that there isn't an easy way to solve this. It just means all the mathematicians who have tried have failed. If you've ever seen the movie Sneakers, so in Sneakers, the premise is somebody has come up with a fast way to do this. And all of a sudden, then any code using RSA is now trivial. And there are methods of encryption that are more secure than RSA. RSA will fall to quantum computing. And so there was some terrific articles a couple of years ago where the quantum computers were finally able to factor 15. And while factoring 15 is not an immense achievement, the idea is that as they get better, they will be able to factor large numbers very rapidly. And codes that are secure now could actually become insecure in the moderate future. So any questions on just the mechanics of how RSA works? This is just telling you, here is the recipe. Why it works is a little bit mysterious. We haven't talked at all about that. But this is the basics. This is what you need to do. And this at least gives you some sense of why this might be a challenge. If we have to go through all possibilities here, we're doing this mod 55. That's my 2 times 5 and 11. If I have to go through all possibilities where n is of size 10 to the 400, we're not going to be able to go through all the things. And so the idea is, so far we don't know an easy way for Eve to use her knowledge of n, e, and x to get n. Now what Eve could do is she could intercept maybe several messages. And if you intercept several messages, could you use that to try to find them? We don't know any way to do that either. The advantage of something like this is Bob can put his stuff publicly. And he can send this to the web and say, if you want to communicate with me, here's how you do it. And you can send me messages in the clear, and I'm the only one who's going to know how to decrypt them. So now imagine Bob gets a letter from Alice saying, oh my God, Bob, I'm in trouble. I need $5,000. Please wire them to this Swiss account. Any Seinfeld fans? The episode where George Costanza refuses to tell anybody his password because he says he won't even tell it to his fiance, to Jerry, and they try to come up with all these elaborate situations where you need to know, and they finally come up with a situation where George has to yell out his password in public or someone will die. You can yell all this stuff, but how does Bob know it's really coming from Alice? So Bob has said, here's how you communicate with me. So what you want to do is you want to do the prolification of subscripts. So I will do P sub B, Q sub B, N sub B. Just put B's everywhere. What do you think the B stands for? Bob. So we put B's everywhere. And so now that's Bob's stuff. All right, well, Alice can have her own stuff. And so Alice, she'll have her own primes, PA, QA, NA, EA, and DA.
But doesn't she use DB?
I'm sorry?
Doesn't she use DB? Or that's to communicate that.
So Bob's stuff will all have a B subscript for Bob. If anybody wants to communicate with Alice, so she will make public her NA, that's going to be public, and her encrypt will be made public. But she will keep everything else secret. And so now, I'm going to just roughly show you how Alice can prove to Bob.
N is 3, right?
For this one? N was 3, yes. So I actually chose a small number. So here's what Alice does. Alice has a message that she wants to send to Bob. And the first part of the message, she encrypts with end Bob and encrypt Bob. And then she has a signature that says, I am Alice, I am Alice. And she encrypts with N Alice and D Alice. Bob starts to decrypt the message, and Bob applies his decrypt. And when Bob applies his decrypt, he's now able to read this part. That's probably not going to be visible. So you apply DB, and that works up to here. And then this is just gobbledygook. But Alice has this stuff publicly available. Alice has made DA publicly available. I mean, her EA publicly available. So what we're really doing is we have M to the E as X, and then we raise it to the D. So this message is really the message to the ED. Well, I can raise it to the ETH power and then the DETH power, or to the DETH power and then the ETH power. You can use either one to encrypt and then use the other one to decrypt. So when Bob gets to this point, and it's still gobbledygook, he can try to decrypt this. He doesn't know how it was encrypted, but if it really is Alice who's encrypting it, then if he uses her public EA, that should undo the DA. And nobody can pretend to be Alice because they don't know what the DA is, and that was used to generate the signature. So as long as you can trust the public website that this is Alice's website, only Alice could then sign the message like that. And so you can then verify who the message came from. Say, no, I went to the Alice page and no, it doesn't work. So this is one of the great advantages of RSA, this ability to digitally sign your message and allow people to know who it's coming from. So we still haven't proven why this works. Okay. Any questions up until now? Yes?
The fact that the M is less than or equal to N.
Right.
So your message...
Well, because we're doing things mod N, if the message was greater than N, since we do mod N, anything that's greater than N, we just chop that off.
So does that literally mean that the number of characters is less than her?
Well, it means I can send numbers from 0 to N minus 1. Those are the messages I can send. So if...
But with each of those representing a letter, so you're essentially saying that your mod has to be more than the characters in your message? Is that
let's say N is 77, so I'm doing 7 times 11.
okay.
I can send as my message numbers from 0 to 76.
But I can send as many of them as I want.
Correct. But you just have to send them one at a time.
I see.
And so it is a little bit expensive to transmit and to encrypt and decrypt. And this is why people sometimes use RSA to send one message first and say, let's do the Vigneri cipher with this as the key phrase, and then you can send the rest of the stuff really fast. And then if you wanted to send another long message, you would use RSA again to send a new key phrase, because you don't want to have repetition. Because if you have two messages that were encrypted the same way with the same key phrase, oh, well, now I can align things like this. And there are games you can play. So a lot of times codes fail because you make very small mistakes in how you implement. The Germans did not implement Enigma as securely as they could have. And some small little mistakes really shrunk the solution space the Allies had to search through tremendously. And so this gives us the formulation of RSA. It tells us what to do. It doesn't tell us why it works. And it doesn't tell us that it's secure. We can't prove that. It's possible that the NSA knows a way to break this. So given that we have 15 minutes left, rather than going into the details of why this works, this was a lot to digest. I'll save the details as to why it works for next time, and just talk about some of the other related problems to this. So we've talked about you being able to sign the message. We've talked about why this is important in terms of being able to verify who you are. We've talked about the need to be able to do things efficiently. We've talked about how important it is to be able to transmit numbers because we can do operations on numbers. There are some other related questions you can do.
Yeah, I had a question earlier about people talking about the level of complexity or the demand of computer time.
Right.
And one of them I had heard was in polynomial time.
Right, so in polynomial time means whatever your key parameter is, it runs polynomial. That maybe your key parameter is n, it'll run like n cubed, n to the fourth, n to the fifth. That's polynomial time.
So what are some of the other
Exponential time would run like e to the n, or 2 to the n.
and factor large
So,
positive numbers?
so right now, we don't know an efficient way to factor large numbers.
So where does that fall in?
I think it follows exponential. So, how fast is factor? I want to say like into the 1/4. Yeah, so they've got sub-exponential. So it's faster than polynomial but slower than exponential. It's like exponential to the cubed root of b log squared b, where b is the number of bits of your number. So if I have a number, if p is about 10 to the 200, well, let's look base 2. Let's say we have a number 2 to the 600. We would say it's 600 bits. And when I'm trying to figure out how expensive an algorithm is, I really want it as a function of the number of bits. So multiplication of polynomials, we look at it as a function of the degree. We saw naively it's like d squared over 2. And then with Horner's algorithm, we saw it's really of size d. And then we saw that if we used fast multiplication or repeated squaring, if we just have x to the n, it's really on the order of log of n. And so the runtime, it's a function of the key parameter. Sometimes the parameter is the degree of the polynomial. Sometimes it's the number of bits of the number. So if we were to do the Euclidean algorithm of x and y was basically like 2 log base 2 of x for the Euclidean algorithm. So if x has 600 bits, this is going to be about 1200. So it's basically going to be twice b of x, where that's the number of bits of x. So the Euclidean algorithm is roughly linear in the number of bits of your number. So it would be a polynomial algorithm in terms of the bits. And that's the right thing to be looking at. So even though the number is huge, 2 to the 600, it's only 600 bits. So it's not that expensive. So I'll end with just some riddles for you to think about for next time. So one of the big things that is related to a lot of these problems is how do you share a secret in public? And again, we talked about how to do RSA, so Bob can post his stuff and Alice can post his stuff. How do you get people to agree on things? And so for a long time it was felt that there was no way for people to come up with a common secret in public. That if people could overhear you, there's no way to do it. And eventually it was discovered that there is a way for two people to just talk with each other, with everybody else hearing, and agree on a mutual secret that only they know. And so, this is related to how RSA works. We'll talk more about this. I'm going to just leave you with 2 problems. So the first is the general problem. I'll do generals. So Williams College has a very small nuclear arsenal. It's not large, not nearly as large as Harvard's, but we have a pretty good one for the most part. They don't want just anybody at Williams to be able to launch the nuclear weapons. You need at least 3 full professors at Williams to agree to launch. So the password is a triple of numbers, A, B, and C. Any three profs can get the triple. No,
Or one piece of it.
no, the triple. So any three professors,
Oh, any three, okay.
any three can launch. No two profs can launch. How do you do this? So, is it possible for somebody to know A, B, and C? No, because if somebody knew A, B, and C, they could launch by themselves. What if somebody knew A and B? Could somebody know A and B?
No.
Well, because if somebody knows A and B, there's got to be somebody who knows C, and then if they get together, the two of them can launch. So nobody can know all three, nobody can know two, so there's got to be, you get one of A, B, and C. So imagine,
You're not saying how many props you're talking about.
so I'll put over here, imagine we have 100 props. So if this is 100, yeah, I like 100.
Yeah, we were estimating 100 seconds in a minute, 100 minutes in an hour.
Yeah, I was gonna say,
Six
it's
hour.
that part, we still know this.
Yeah, I know, 100 hours in a day.
Anybody a fan of the old movie Other People's Money, Danny DeVito, Gregory Peck?
No.
Another movie,
Familiar
great
with
mind.
the scandal.
I'm sorry?
I'm familiar with the scandal that it was based on, but I haven't seen the movie.
Okay, great movie, but there's a nice line, I like nice round numbers. And so they replace 125 million with 100 million just to make the calculations easier.
Yeah.
So imagine there's 100 profs. So if you're going to assign A, B, and C to them, here's maybe it goes A, B, C. What does the fourth prof get?
A, B.
Well, if the fourth prof gets A, then profs 1, 2, and 4 wouldn't be able to launch.
Right.
So the fourth prof can't get an A. The fourth prof can't get a B because then B, C, B wouldn't be able to launch. The fourth prof can't get a C.
Oh, any three can get the triple?
Any three.
Oh.
I don't understand that.
How could
Any three can do it, then why can? Any three, you mean any group of three?
Any group of
Not
three.
any
How
group.
could that be?
That's why there's a problem here. There is a way to do this. There is a way to do this. There is a way to assign information. But you are looking at the problem the wrong way because I'm trying to get you to look at it the wrong way.
Yeah.
So the hint is you can't assign A, B, and C to the props. You have to do something else.
Right.
Because if you just assign A, B, and C, you're stuck. There has to be some other way of giving information such that when they get together, they can figure out what A, B, and C are. Okay? So don't say it out loud.
No, I was just guessing that.
Don't say it out loud. Don't say it out loud. So you want to assign information in a way that whenever three get together, they can do it.
Figure out A, B, and C.
But no two can do it.
Right.
Okay, so that's one.
Okay.
The next one, I'll do the old pirate marriage problem. So you have two islands. And on one island, you have one person, and on the other island, you have the other person. And you have a pirate ship. There's our pirate ship. The Dread Pirate Roberts on his pirate ship. Anybody know the pirate ship? What is the name of the pirate ship?
Revenge.
It's the Revenge. Very good. It's the Revenge. So he's a somewhat honorable pirate, as pirates go. And they each have a lock. And they each have a key to their lock. And he wants to propose to her. So he wants to send a ring, because he somehow has ended up on the desert island with a very nice engagement ring. And the pirates will transport things back and forth. And the pirates have a nice box, and it has places for two locks. And each one has a lock, and each one has a key. and they're different keys. So her key only works on her lock, his key only works on his lock. The pirates will transmit things back and forth. If it is unlocked, the pirates will open up the box and take whatever's in it. But if the box is locked, the pirates will leave it there. So the question is, how does he get the ring to her? This is equivalent to the problem we are trying to solve. How do you have two people in a crowded room agree on the secret? What's the secret? So in this problem, what would be the secret?
The ring in the box.
The ring in the box. And so is there a way for them to agree upon the secret so that they can both see the secret, but nobody else will? Even though everything they're doing, they're making this is like a magician who says, I'm going to have you in the audience come forward, and I'm going to make you part of the act and still fool you. So the question is, how do you do that? So these are two great riddles in terms of trying to explain what's going on. There's lots, but we'll do one more riddle just so that you have plenty of things to think about. No problem. No problem. Take care. So there's lots of versions of this one. I'll do this one. You have three people, and each person can only see the other two. And you have hats placed on them. Each hat, 50% of the time is white, 50% of the time it's black. Do you want the grim, ghastly version, or do you want the cleaned up version? Grim. So if even one person speaks, says the wrong hat color, all three people are killed. If everybody speaks, then if everybody who speaks is correct, then not only does everybody live, but everybody gets $1 million. So one strategy you can come up with is one person just always speaks and everybody else is silent, and this person always says white, or the person always says black. And then you'll be right half the time, and you'll be wrong half the time.
And they're guessing their own hat,
So they are saying their hat color.
but they can't see it.
So basically your eyes are closed again, 1, 2, 3, open. And then you have 5 seconds to look at the other two people, and then based on what you see, you say either white, black, or you're silent. And each person has a 50-50 chance of having a white or black hat independent of everyone else. And if even one person who speaks is wrong, everybody's killed. If everybody who speaks is correct, everybody lives and everybody gets $1 million. So again, don't say the answer, don't say the answer.
I don't know the answer, but if you have 3 like that, the black hat always knows that he has a black hat.
No, you don't know, because each hat is equally likely to be black or white.
Not 50% of the hats are black.
Correct. So each hat is chosen independent of all the others. So for each one, I flip a coin, and then I use my Microsoft Paint, and I paint it either white or black. And so the question is, we already have a strategy that will work 50% of the time. Just one person is special, and that person always says white, or that person always says black. They get to talk ahead of time what strategy. And these are 3 mathematicians, so they're extremely intelligent people. And they will come up with the best possible strategy. And so the question is, what strategy should they use? And the solution to this riddle is related to an important question of when you transmit information, how do you make sure that the person receives what you transmit? So imagine you're sending strings of zeros and ones. It would be really bad if somebody receives a 1 and you meant to send a 0. So if you could, what would be the best probability of success for transmitting a digit?
Either it's on or it's off.
So what would you like your percent of being right to be? 100%. What's the worst percent?
0.
No. 50. Why is 0% good? If you're always wrong, then you're always right. Just take the opposite. So if you know that you always receive the opposite of what I intend. So there's a beautiful Seinfeld episode called The Opposite, where George is bemoaning how every decision he's made in his life is wrong. And so his friends convince him to do the opposite and just see what happens. And it's incredibly funny. You know, at one point he's now interviewing with the New York Yankees, and the owner Simon says, "It's a pleasure to meet with you." I wish I could say the same to you, but I just mouthed off against signed them. Someone's like, hire this man! This only works when you have binary life decisions. You know, if you really only have two options, then yes, knowing that it is wrong is equivalent to knowing what the right answer is. Most things in life are not binary. But it turns out that the solution to this riddle is related to how do you quickly transmit information and make sure that the person on the other side is receiving it correctly.